Ever since humans began building things, and that's a long time ago, we've been using this stuff around us: rocks, trees, dirt. Eventually, we figured out how to turn some of the rocks into concrete and get metals out of that dirt. But now we don't have to make everything out of the materials that are just sitting around in the environment, but can engineer entirely new materials that might be better. Houses that replace the 2x4s in their walls with carbon nanotubes, or something else that won't rot or be eaten by termites, or compounds with properties we haven't even thought of yet. I'm Seth Shostak.
I'm Molly Bentley. Welcome to Big Picture Science, produced at the SETI Institute, where researchers investigate the nature and origin of life. On Big Picture Science, we step back to get the wide-angle view on science and technology, and in this episode, we are living in a material whirl of new stuff with which to create the buildings, medical devices, and spacesuits of the future. From nearly as strong as steel composites to superglues drawn from the protein of dangerous bacteria, the concept of man-made material now goes far beyond plastics and almost anywhere your imagination can take it. This episode, it's in material.
Engine running. Liftoff. We have a liftoff.
When we think of the future of materials, it's natural to tilt our heads toward the sky and consider the exotic materials used out there in space. NASA has always been a few giant leaps ahead in seeking out and developing endurable, performance-enhancing modern materials to deal with the rigors of space flight and the safety of its astronauts. For the materials they choose, failure is not a desirable option.
I mean, space is one tough work environment.
Welcome to Space Depot, where ethereal material is thrice the price. Can I help you, sir?
Yeah, I'm looking for a structural material that can withstand friction at 17,000 miles an hour, radiation from high-energy particles, and temperatures below minus 300 degrees Fahrenheit.
Ah, you'll want our carbon composites. This way.
Strong, durable, and the light gray is nice. But can you do it in a canary yellow?
No superlatives are too outrageous for NASA when it comes to building for space. The agency uses carbon nanotubes and other composites that are the strongest, the stiffest, and have the highest electrical and thermal conductivity. It uses the most space-resistant polymers that combat erosion and the most durable vacuum-sealed plastic pouches to hold powdery tang, which, by the way, NASA did not invent, but did make cool.
As our goals for space exploration have changed, materials have evolved. Ever more sophisticated technology has allowed us to build ever more sophisticated spaceships and spacesuits.
Astronauts have always been made of the right stuff, as have their spacesuits, until now. The astronauts are still exceptional flight specialists with outstanding mental and physical stamina. But if the next generation of them wants to go deeper into space, to Mars, for instance, their NASA-issued pressurized onesies won't cut it.
Nicole Stott is a retired NASA astronaut who last rocketed into space in 2011, although the view from a couple hundred miles up will never be far from her mind.
The view is stunning, and you develop a new appreciation for your home planet with that perspective.
We got her perspective about the future of spacesuits here on terra firma. A veteran of 2 spaceflights and 104 days living and working in space on both the Space Shuttle and the International Space Station, she was at the 2017 Space Fest to discuss how to reboot the suit for a new generation of space exploration.
Yeah, my first flight was what we called a long-duration space flight. So I went up on a shuttle, STS-128 Discovery flight, and then I spent a little over 3 months on the space station as part of Expeditions 20 and 21. And then I came home on Atlantis, STS-129. Then about a year and a half later, I flew on the final flight of Discovery, STS-133.
Nicole, I want to ask you about space suits. Now, did you have to wear a spacesuit when you went up into the ISS?
Well, we wore a spacesuit as part of our launch. You know, when we launched on the space shuttle, we had our ascent entry suits on, those orange suits that are, I think, pretty well known. And then once you're on the space station, though, or actually once you're up in space on the space shuttle, it's a pressurized environment. It's like, sea level pressure. So you just wear your normal clothes inside of the spacecraft. And the same thing on the station. And then the only other times you need a spacesuit are if you're going to go outside and do a spacewalk, or if you're getting ready to land and come home.
Now, you've been part of a panel here at Space Fest entitled Rebooting the Suit. It sounds like something for, I don't know, Brooks Brothers or Hart, Schaffner and Marx. So rebooting the suit, what's wrong with the spacesuits that we have?
I don't think there's anything wrong with the spacesuits that we have. We've certainly learned lessons about the structure of it, the engineering behind it, and those kinds of things. That for what we do now on the space station with the spacewalks that we do to repair or install new things on the station, it's fine. But when we start talking about doing more surface exploration, where you're walking around, for extended times on the surface, the suit we have right now won't support that. When we talk about living longer periods of time in a place where you're in a suit a lot, it's just going to need to be a different thing. It's going to need to be more flexible. It's going to need to be more resilient, I think, because it's going to be working hard a lot longer.
Okay, so what is the problem? The problem is not one of safety, I assume. It's not that after 10 hours in walking on the surface of Mars, the conventional suits would suddenly become dangerous. It's just that they don't allow you the flexibility to do your job?
Yeah, the structure, kind of the build of the suit that we use right now, those big white suits that we use on the station for our spacewalks, they're designed for you to be floating most of the time, for you to be translating with your hands from one place to another. You're not walking anywhere in those suits. They're not built to walk in. They're built for you to move with your hands and for you to then put your feet into a foot restraint somewhere and be held in place. But to walk in those suits they're just not designed to do that.
Okay, so we need a better suit if you're going to, for example, be wearing a suit every day on Mars. If you go to Mars and you stay there 6 months, you don't go outside without a suit.
Right.
And the suits we have today just aren't going to cut it. You'll want to get back inside after a short period of time.
Yeah, they're just not designed for what you would be doing walking around on the surface of a planet. They're just not those suits.
Okay, so what's the secret to building new suits? I mean, is the improvement likely to come from the new materials then? Or is it just better engineering because we've got some experience?
Well, I think it'll be a mix of those things. And from an engineering standpoint, we talked a little bit about the 3D printing aspects of things. If we can make the process for building and repairing suits, having the capability to fix them more efficient, then that'll allow us a little different kind of flexibility in the materials that we have available to do these things. There's a lot of research being done into it. One of the people that most of us know, Newman, who was our deputy administrator for NASA for a while. I mean, she's at MIT and has been doing a lot of interesting research over time on this funky looking, what you would think of as spacey, futuristic looking version of a suit that at this point isn't going to do the job. But the technology that they're investigating, the evolution of what they're doing in that design and thinking about, I think the way they're looking at it is like, if we could have it however we want, it would be like this. Now, how do we get there?
Nicole Stott, thank you so very much for speaking with us.
Absolutely. Thanks for the interest. I appreciate it.
Nicole Stott is an artist and a retired NASA astronaut.
Hello, I'm Professor Deva Newman, the Apollo Program Professor of Astronautics at MIT.
Hey, Deva, former astronaut Nicole Stott says that you have and she puts it this way, funky-looking, spacey, futuristic-looking version of a suit. Is she right?
Yeah, she's absolutely right.
What does this suit look like?
Well, it's imagine shrink wrapping an astronaut or yourself. So it looks very different. All traditional suits and every suit that's ever flown is a gas pressurized. So you're kind of in a balloon. It keeps you alive. My biosuit uses a different technology. It still has to pressurize you to keep you alive, but we apply the pressure directly to your skin. So that's called mechanical counterpressure.
Now, the big, bulky, pressurized suits that we readily associate with astronauts are filled with gas. This one is not, but it's still applying a kind of pressurization. And why is that important out there?
Because our physiology, we can't survive in a vacuum. So you have to have pressure on your skin. We have to be pressurized. We just kind of take it for granted here on Earth because we're living in a 1-atmosphere environment. And if you're in an unpressurized environment, then the suit has to provide that pressure for you. The huge advantage of the biosuit is for planetary exploration because it's a much less massive suit, on the order of a magnitude less massive. You're very mobile. I'm trying to make the explorer like an Olympic athlete, give them all the flexibility in the world to explore Mars.
Okay, so instead of climbing into a bulky pressurized suit, this is more like getting into maybe a diving suit or something that hugs your skin.
Exactly. So it hugs your skin, applies about a third of an atmosphere. That's about 30 kilopascals, 4.3 psi. That's the pressure you need to stay alive, in the vacuum of space. And thinking about a wetsuit or a tight-fitting suit is kind of the right look. She says it's a funky look. I think it's very aesthetic and beautiful. We pay a lot of attention to not just the mathematics and engineering, but then also really the aesthetics.
Well, when we talk about hostile environments, are we speaking to you outside? I think I'm hearing airplanes go overhead. Is that right?
Absolutely. Yes, we are. That's a real authentic background airplane. It's a small airplane. People are aerospace engineers when they look up at the sky for every airplane they hear.
Okay, so we have the streamlined second skin. Now, I want to get to some of the nifty components that help it retain its shape. But what is the stretchy material that gives it its structure, or can you not tease one from the other?
So that's a great question because our inventions and my patents are about the materials and the design. First, you can use passive elastics. What that is a stretchy elastic material. Kind of think spandex, think kind of an inner tube tire, if you will. We measure the material properties that we need to get this compression, get this pressure on your skin, but still be comfortable. So first layer, passive elastics, we call that. And that gets you about 20% pressure production, 20% of an atmosphere, but I want to get to 30%. So I need 10% more. So how we do that is with active materials. So those are polymers. Polymers just really made up of many molecules that you string together to make a long chain. And then the beautiful thing about polymers is you can specify material properties that you want your material to be made out of. And the polymers follow the patterns of the suit. It looks like a Spider-Man suit. So that's why Nicole probably says it's funky, it's great. It looks like Spider-Man. I've actually been working on this research a lot longer than the Spider-Man movies have been out. So that's just three-dimensional eigenvector math that drives what we call these lines of non-extension, and that makes the patterning of the suit. So I guess it's good to think about it kind of like an internal skeleton, if you will. If you think exoskeletons, again, they're usually big and bulky and mechanical electrical systems. This is a, second skin right on your skin, but this patterning and this three-dimensional geometry, we kind of dial in, again, the material properties that we want. So you put it on, but again, it's going to be much more like clothing, right? You put it on, you want to cinch it up a little bit. Well, how we cinch that up is by using actually some shape memory alloys. So those are active materials. So it's kind of proper to think about those as active zippers, if you will, to give us our full production. Because spacesuits, big challenge with spacesuit design is donning and doffing. That just means putting it on and taking it off.
Donning and doffing?
Yeah, those are spacesuit words for we have to have our words for everything, right? So donning and doffing, exactly. Putting a spacesuit on and taking it off.
Now, you said polymers, and then you talked about shape memory alloy. Now, an alloy is a metal that's formed by combining other metals. Is that right? Can you say more about those?
We studied every active material out there. There's a candidate list of 14 top ones, and we ended up on shape memory alloys. And you're exactly right. That's a combining metals, and so sometimes they're called artificial muscle wires. They're nickel and titanium, the metallics these active materials are. So it really is the second skin notion. I mean, it's a skin tight suit. It fits right on your body, on your skin.
Well then, David, how do you take this, or as you would say, doff a biofit suit? How do you get it off?
There you go. So you just jump into the biosuit, very comfortable, get in quick, cinch it up a little bit, and then to take it off, you do the reverse. You'd release a little bit of the active materials, and then you just take it off almost like normal clothes.
Well, finally, David, you have a passive fabric working with active materials, and it gets to the larger question of the role of smart materials. NASA has always had smart materials, but even smarter materials, living materials, in the future of space exploration. And what is the future of material science as applied to space?
it's phenomenal. I think it's critically important. I think it's some of the revolutionary technologies we're looking for really are, let's say, living materials. All in all, my biosuit design, I am trying to copy nature. Nature is designed, I think, humans and most plants and animals pretty exquisitely. So it really is biomimetics. I'm trying to say, wow, how is the skin even designed and work as an organ? And that's kind of lots of our inspiration for the biosuit.
David Newman, thank you so much for speaking with us.
Thank you, Molly. Great to talk to you.
Deva Newman is a professor of astronautics and engineering systems at the Massachusetts Institute of Technology.
Coming up, NASA hasn't cornered the market on futuristic materials or those that are inspired by biology. One exceptional example can be found on the web, the one that's in the corner of your attic.
It's In Material from Big Picture Science. Okay, NASA has a pretty impressive research and development program, but there's one R&D effort that's even better. With oodles of time on its side, evolution has produced some of the most well-adapted and strangest materials ever.
Spider silk is deceiving. You can easily remove these gossamer threads in your attic with a wipe of the cloth, but they are remarkably strong. Spider silk is not stronger than steel, but its tensile strength, that is, its resistance to breaking under tension, is comparable.
It's a protein fiber that's really tough on a molecular scale. Spider silk is handy, and it's effective if your day job is catching flies. So you can forgive the spiders for not wanting to give it up to cooperate with lab-coated researchers.
The challenge with actually using regular spider silk is that spiders don't particularly like to give it up. They don't give up an awful lot of it. And if they're put in combination with other spiders, they tend to get cannibalistic and eat each other and don't actually work very well.
Since spiders prefer to be solitary spinners, scientists are finding ways to synthesize spider silk. According to Andrew Dent, Vice President of Library and Materials Research at Material Connection, a consultancy firm that seeks out promising new materials for designers and manufacturers.
But the silk production needs to be scaled up. Andrew Dent says researchers are finding a way to manufacture the silk in larger quantities by putting spider DNA into another animal.
They've tried putting it into the DNA of goats and milking the goats. They've tried putting it into silkworms and having the silkworms produce silk in the same way they do. But you can also make it out of things such as E. coli bacteria and also yeast. So take the DNA from the spider, replicate that into something which can produce larger amounts, and then produce that.
Well, wait a minute. That sounds like the movie Spider-Man, right? Somehow the guy gets bitten by a spider, presumably injecting some, DNA into him, and suddenly he can make spider silk coming out of his palms.
It's kind of the same way. Not quite as simply as just squirting it out of your wrists. It does take quite a bit of complicated chemistry, but it's essentially the same thing, yes.
Okay, so now what are the properties of spider silk? I mean, why would we want to make it in goats or bacteria or some other critters? Why do we want industrial quantities of this stuff?
Well, as you mentioned at the start, it has great tensile strength. As you also correctly said, it's about as strong as regular steel. The advantage is it's about a sixth of the weight, though. So for the same weight of material, you are getting 6 times stronger, even though in total volume, it's about the same. So you're getting a much more lightweight material. Its elasticity, how much it stretches, is quite amazing. So think again about Spider-Man swinging through Manhattan. That stretchiness is very effective. It means it's less likely to snap. It also means it has properties that makes it almost like a Kevlar, which is a great energy absorber. One can imagine this material potentially being used in things like bulletproof vests, because bulletproof vests aren't the strongest things around, but they certainly are the most energy absorbing. So when an impact hits, rather than breaking, shattering, or transferring the impact through to you, it absorbs it all and therefore protects you.
Are there any applications that take advantage of the fact that it's maybe comparable in steel to tensile strength, so you're pulling on it and doesn't break, but that don't involve weaving it into a jacket? What else could I use it for?
It's actually being used in the medical industry, potentially for sutures. So another advantage of this is that it is also potentially biodegradable. Adidas has come out with a shoe that's almost entirely biodegradable that they are using synthetic spider silk for. So you can actually use it potentially to put into the body, sew something up or hold something as part of a medical procedure, and then eventually it will dissolve. So it has that advantage. It's also being used in cosmetics as well. We're finding people using it or trying to use it as a way of skin tightening because the material itself can come in very, very fine fibers, much more fine than, say, a human hair, but actually has good tensile strength and good elasticity. So imagine putting that onto the skin, it's able to keep the skin tight and taut, so actually potentially reducing wrinkles and improving overall skin look. So it's actually finding some applications in cosmetics too.
All right. So it sounds like there are various applications, all of which kind of sound interesting. Is it sticky? I'm speaking now of synthetic spider silk, presumably made using other animals. I mean, could I use it to catch mosquitoes, for example? I mean,
well, the majority of the versions that are out there, they're trying not to be sticky. The cosmetics has an advantage if it is sticky, and there are certain ways to produce it where it comes out of water or out of a solution where you can maintain that stickiness. But mostly you want to avoid that because, stickiness is good in certain applications, but for the majority of the current applications they're using it for, they want it relatively dry and feeling kind of nice because, as you mentioned, people are manufacturing jackets out of it. There's a new tie that's being sold by a company called Bolt Threads, which is entirely from synthetic spider silk. As I mentioned, the running sneaker. Also, the US Department of Defense has recently taken a whole shipment of synthetic spider silk that they can potentially try to use for applications in armor and bullet-resistant applications.
all right. So there are already applications out there. Now, you've mentioned that the manufacturing process, at least as you've described it, involves, injecting DNA into other animals. It's sort of like surrogate motherhood, surrogate spiderhood. What is actually in spider silk? I mean, if you looked at it with a big enough microscope, what would you see inside? What is it that makes spider silk spider silk?
It's basically a protein, but it's the ability of the spider to control what the protein is and how it is actually produced that enables it to make different types when it needs to. There are other protein fibers out there. There are fibers that come from collagen. There are fibers that come from milk as well. The advantage that spider silk has is that its protein has just proved to be incredibly strong because it needs that strength in order for it to catch prey and also to survive. So plenty of other protein-based fibers out there produced from natural resources, but the spider has the protein version, which has the best properties for what we're looking for.
My first reaction when I hear about attempts to, if you will, co-opt something in nature, particularly materials or the arrangement of materials like, gecko feet or whatever, I'm thinking, gosh, do we have to go look at lizards to figure out how to do this? Can't we do better? We're a modern technological society. But then I'm thinking, well, the gecko feed or the spider silk, that's the result of hundreds of millions, in some cases billions of years of evolution, bottom-up engineering, with only the better products surviving in the marketplace called nature. And so maybe they've come up with solutions that, that they spent 100 million years working on that we can't replicate in the lab with 10 years worth of work. Are there other bio-invented technologies that Material Connection is trying to, bring into the market?
You're totally right. Nature has had a long time in which to develop these. The good thing about that means that they end up with incredible solutions which are perfect for the ecosystem in which the animal or plant lives. It also has zero waste as well. Think about it. All of these amazing innovations come with zero waste. The spider doesn't create a whole bunch of packaging, doesn't require a whole bunch of energy as well to do what it does. Same with gecko feet. So, yeah, there are other things. We've seen recently packaging materials made out of mushrooms. There's a company called Ecovative that is producing packaging like foam structures that can be used to ship computers, can be used to package up furniture and shipped across country, but is manufactured from mushrooms. And the advantage of mushrooms, of course, is that they can grow in the dark with no fertilizers, with virtually no water. So you can produce these foam parts very much like expanded polystyrene on a factory floor, simply just by putting mushroom spores around some agricultural waste, and they'll grow in a few days, and you end up with this great packaging material. That one's one we really love. Another one is leather alternatives using bacteria, again, to produce in the same way that they do for the spider silk. If you feed bacteria sugar, they secrete. In the case of spider silk, they tend to secrete a certain type of protein, but you can also get them to secrete almost leather-like materials. And we're looking at materials such as that for alternatives to leather, because of course leather has a source which not everyone agrees with. So it's an alternative to leather, but it's produced by bacteria. We're not so concerned about whether bacteria are treated well at the moment. So it's a great source for that, and it has wonderful applications, again, in cosmetics, but also in apparel and potentially also in other industrial uses.
Andrew Dent, thank you so very much for speaking with us.
You're welcome, Seth. Good to talk to you.
Andrew Dent is Vice President of Library and Materials Research at Material Connection.
Hey, my new octa-core 50 gigahertz laptop has arrived.
Hey, whoa, don't throw that packaging away. Bring it into the kitchen for lunch. I'll make it into soup.
The next innovative material, inspired by biology, turns a potential enemy into a friend. Let's just say, who needs imaginary monsters when here on Earth, and perhaps living in you right now, are flesh-eating bacteria?
The flesh-eating disease is caused by a bacterium, Streptococcus pyogenes, that can cause other infections such as strep throat and scarlet fever.
This bacterium is very, very common, and actually nearly all of us will have been infected with it at some stage in our lives. Many of us will be carrying it. It often lives in people's throats.
But usually your body fights it off without serious consequences. This bacterium presents another opportunity for scientists to take advantage of evolution's R&D program. Dangerous bacteria and viruses have evolved effective adaptive tricks to thwart ongoing threats from the body's immune system.
Scientists have isolated one of the tricks of Streptococcus pyogenes, a protein that helps it infect cells, and they hope to turn it into a medical superglue. We'll hear about that, but first we asked Mark Howarth, one of the Oxford University biochemists working on the project, about the possible PR challenge of developing a medical device made from flesh-eating bacteria.
Okay, so nothing's alive that we work with. So the wonder of genetic engineering is that we can take a quite scary bacterium that has the potential to cause these diseases, occasionally this flesh-eating disease, and we can take interesting components of that, and then we can make them in any system we like away from the dangerous organism, so we can make it entirely safe.
Well, before you describe how you engineered one of the proteins produced by this bacterium into a superglue, I mean, how did you? What did you notice about this protein that attracted, so to speak, your attention?
Yeah. So the initial breakthrough was actually made in New Zealand by a scientist there called Ted Baker. And he was studying these bacteria, and he was studying how they manage to stick inside the body. They live in the throat, and that's quite a hard place to make your home because there's a lot happening there. You've got mucus in your throat, you've got sort of things washing past the cells that it's trying to stick onto. And so what he did was he isolated some of the genetic elements from this bacteria. He then expressed them in huge amounts, and then he shone X-rays at them. So he made a little crystal of them, shone X-rays at them, and through that process that's quite well developed now, we're able to actually see where every single atom is in these proteins. And so that's a standard process, but when he looked there, he found something that was really, really strange. A very unusual thing had happened in this protein that essentially had managed to lock this protein unit together. So in our cells we have thousands of different proteins, and these proteins are often only slightly stable. So they kind of get outside their comfort zone and it all goes horribly wrong. And it's like you're probably familiar when you have an egg and you cook it, it goes from clear to white. What's happening there is it's all sort of clotting and gumming together, and these proteins are getting very disordered. So that's sort of the standard process, but in this bacterium there's a lock that holds this protein, so you can do these horrible things to it. You can heat it, you can put it in a very different situations compared to what organisms would normally encounter, and it manages to hold itself together. So that was the trigger for us to come in. And we thought that this very unusual chemistry that you find in this lock could be adapted into a glue. This was done by a graduate student, Bijan Zachary, working in my lab. And he found that he could split this protein into two parts. And these parts, these are called spy tag and spy catcher.
All right, so from Streptococcus pyogenes, you get SPY or something like that, right?
Yeah, exactly.
Okay, what you found was that within this protein, there was a kind of a bond in there that was very, very strong, much more so than in, your run-of-the-mill, protein or something. And he was able to split that bond and make these two pieces.
Yep.
Now, let's talk for a minute about how this works. But indeed, how glue works. Most people don't think about it. They just squeeze it out and use it. But, some of it functions kind of like, cement, right? You squeeze out some goo from the glue, and when it hardens, the two things you're gluing together become trapped, and so they kind of stick together, but it's all dependent on that cement. That's pretty simple, but that's not how your glue works. It isn't that it's making some sort of, matrix of gunk that hardens.
Yeah, so it's really precise. So we know exactly the atoms that are reacting, and superglue is one analogy. It's not a perfect analogy because we all know when we try and fix a cup or a chair with superglue, we drop it on the floor and then it'll break again. But with our superglue, we've actually found that there's nothing you can do to break it apart. So this is a protein superglue that, as far as we know, will stay stuck forever.
And the mechanism there is what's called a covalent bond. Is that right?
Yeah, exactly.
All right.
So it's a covalent bond, and it's one of the most stable covalent bonds you can form. One of the reasons that it's quite special is because, as I said, this is a kind of chemistry that you find in this bacterium, but you don't find it in many other places.
This is not mechanical, right? When I think of proteins, I don't know anything about proteins, but I imagine these pictures you see in the magazines with complex things that look like rats' nests, and some of them can kind of fit into other proteins like puzzle pieces, and that always strikes me as rather mechanical. It's just like a lock and key kind of thing. But this is an electronic, if you will, attraction there, and you say this is tougher than nails.
Yeah, spot on. So that's a really good analogy that you have these puzzle pieces fitting together, and often it's that shape matching that's the only thing that's holding it. And so that may stick for a second, it may stick for occasionally half an hour, but what we can do with our glue is, as I said, we can stick it forever.
Well, I think listeners might be thinking, okay, this is what I need to repair that chair leg, right? Because I'm not likely to boil it in hydrochloric acid or anything else. But that's not the kind of application you're looking at here. What are the applications?
So the one that we're most excited about is its possibilities to speed up the way that people produce vaccines. And the one we focused on particularly is malaria. So there are about 200 million cases of malaria each year. There are drugs that are effective against malaria, but it's just so hard to get them to everyone who needs them. So where does the spy tag come in? Well, when you give a vaccine, what you want to do is make that vaccine look just like a virus. So if you can make it look like a virus, but not be alive, not be infectious, then your body takes it really seriously and you generate a lot of antibodies, and those antibodies can last for the whole of your life if you do it well enough. And so people have been trying to do this, and it's been really, really difficult to take the malaria proteins and make them look like a virus. And this superglue is a way to do this really easily.
The bottom line here, from the standpoint of a layperson, is that, here you have a component of a flesh-eating bacteria, which doesn't sound like it's going to help your health very much, that can be engineered into a product that can go into your body, do no harm, and in fact do you some good. That's quite a story at a dinner.
Yeah, I hope so. It's very exciting to be involved in this.
It does sound like you're trying to take advantage of literally millions of years of research and development, which you didn't have to fund yourself.
Exactly. Yeah.
Mark Howarth, thank you so very much for speaking with us.
It's been a great pleasure. Thanks a lot.
Mark Howarth is a biochemist at Oxford University in the UK.
So in both cases here, we have a kind of technology, if you will, that's been developed by nature for very specific purposes, whether it's, trapping food if you're a spider or just holding on to things that are passing by you in the throat of some person, that can be exploited because now we can take that technology and put it to work in the lab or in the factory.
Up next, going beyond the materials that nature has produced.
It's In Material from Big Picture Science. As we consider the materials of the future and what we could make with them, well, how could we not get some perspective from this guy?
I'm Mark Miodownik. I'm Director of the Institute of Making at University College London.
The Institute of Making, how great is that? Just saying its name starts the creative juices flowing.
But that cool title, plus the fact that Dr. Miodownik is a materials scientist himself and the author of Stuff Matters, Exploring the Marvelous Materials That Shape Our Man-Made World, and the recipient of the 2017 Michael Faraday Prize for Excellence in Science Communication in the UK, none of that seems to preclude indifference to materials science on the part of his incoming students.
The preconception they have is that it's a kind of quite dull subject which they have to learn because they have to know about it because everything is made of something. And so all aspects of engineering, all aspects of architecture, art, all rely on knowledge of materials. So they kind of have to do it, but they sort of think it's going to be boring. And what I wanted them to take away at the end of it is that if you want to understand materials and be an innovator in any field, fashion or wearable tech, healthcare, it's not a theoretical subject. At its heart, it's about making things. And that is also what's so enjoyable about it.
Well, indeed, it's not dull. In this century, we're going to see a revolution in materials. New materials that go beyond what nature has given us, even beyond such dramatic developments as harnessing the adhesive properties of a bacterial protein.
We will create materials that have never existed. We've already done so with carbon nanotubes. We'll turn this process around. Instead of looking at existing properties and working with them, we'll ask, what sort of properties do we need in new materials? And this may change a lot of things because, after all, almost everything we build still uses old materials.
Mark, when I look around this place, I see a parking lot filled with cars made mostly of iron, a building with some glass, wood, and stone, some streets out there paved in tar. That wasn't much different 100 years ago, or even 1,000. I don't see too many man-made materials here. We still use the same stuff the Romans used, right?
Well, yes, we do. The Romans were pretty clever. They invented concrete and they didn't invent glass, but they worked out how to make glass on an industrial scale, and they invented the glass window. So, yeah, the Romans gave us a good start, but we have improved a bit.
So you don't figure we'll always be building our homes with, sawed up trees, for example?
Wood is an incredibly amazing material. It's mostly made of, a kind of plastic lignin and kind of glue, a fiber, so a bit like carbon fiber. It's a strong fiber to reinforce the structure, and air. So it's a composite. I think probably you're right, though, that we'll move away from using it as a major construction material, and we'll probably replace it with something like a carbon fiber composite, but hopefully, and I think this is on the cards, something based on graphene or carbon nanotubes.
What would be the advantages? One nice thing about wood, I will say, is that it's, you can knock a nail into it at any point. You can saw it up, on site with pretty simple tools and that sort of thing. Would that be true of carbon nanotube, beams in my house?
You're right. No, at the moment, the way they are made with epoxies, and they don't tend to kind of react very well to having a nail hit through them. But we're in the early days of these synthetic composites. You have to remember that when you build big, you also make heavy structures, and they are under a lot of stress. especially if you build tall, they end up with a lot of wind stress. And so we'll need much higher spec materials for those type of structures.
There are a lot of new materials, seemingly, that, derive from biology. And in this program, we've talked about materials inspired by spider silk and even bacterial proteins. Is it legit to call those man-made materials, or does it even matter what we call them?
Yeah, what is a man-made material? I mean, in some ways, all materials that we've kind of extracted in some way. I mean, wood is essentially a man-made material, even though it is of course bio-made, because we've shaped it. And if you've ever tried to cut a tree down with a flint axe, you'll know quite how difficult it is to turn a tree into an actual functional piece of material you can use. So to me, the man-madeness is that transformation of a living organism into a material that you make something out of. So yes, I think it's fine to call them man-made as soon as we make something out of them.
Now, it seems to me, Mark, that there are two reasons to engineer new materials, and one is to make something better than what we can chop down or mine or whatever, and two, to replace stuff that's getting low. What's getting low?
Yeah, well, there really isn't, on the face of it, anything that's getting low, because we live on a huge planet. I mean, I know it seems crowded, especially in London in the rush hour, but we are on this tiny thin sliver of the crust, and even so we've only dug up a tiny amount of it. So in some senses, if you just calculate how much tonnage of every single element that you'd want to use in the real crust, let's say even just going 300 miles down, there's just more than you can ever conceive that we'll need. But the problem is getting it out at a reasonable cost, and a cost in terms of the environment, i.e. how much energy we're going to use. So for me, the only way to answer this question is about whether energy becomes cheap in the future, and I mean cheap in terms of sustainably cheap, or whether it's expensive in the future. And if it's expensive in the future, if energy turns out to be renewable but expensive, then quite a lot of things are going to get scarce for us. Pretty much all the rare elements are going to become really difficult to get out of the ground at any reasonable cost.
What about mining space? Maybe salvation lies in the asteroid belt, or at least some nearby asteroids. That way you don't have to dig too deep down into the ground. Maybe it's cheaper just to pull the stuff in.
Yeah, well, so I think we will mine space, but I don't think we'll mine it in order to bring it back to Earth. And the reason for that is it's such a large cost to get anything up into space and back down again. So it's something like $1 million per kilogram to get something to the moon. Now, if you think of any sort of cost of any of our materials, that's way out of the range you'd consider as being economic. But when we're in space already, i.e. trying to build a moon base or try to build a base on Mars, it will make absolute sense. In fact, I think it will be essential to mine space in order to build those civilizations, and I think that is worth thinking about now just because of that, because it's so essential to that exploration.
Mark, you paint the picture of a world that is largely synthetic. Can you take us to that world? Can you describe what we'd see if we walk down the street of a city in, say, 2070, 50 years from now?
I think the big themes will be what people look like. So I'm quite convinced that the desire to live longer and to have independent mobility longer will mean that people's wearing exoskeletons that are either quite visible or, semi-visible will be one of the striking features of the future. You will not see old people hobbling down the street with a stick, or probably you won't see them even in wheelchairs. People will be walking, and they will have quite a lot of kit on them, motors and exoskeletons. And the reason I'm quite certain about that is because A, it's doable. It's almost doable now. There's a few small things that have to happen, and B, people really want it. So you put those two things together, and that is the history of human race. We when we really want something, when we really desire it, we're very good at getting it. So I think the street scene will be one of people having various different augmentations
What do you see as the role of aesthetics in future materials? I mean, you make the case that materials play an emotional role in our lives in the way that sitting on a couch elicits a different feeling than sitting on a, cold metal stool. We have comfort foods. Are we going to have comfort materials?
Yeah, it's funny because comfort and aesthetics go together with fashion as well. And I think the exciting thing about the future is that you just don't know what type of thing that we're going to really go for. But the fact that the buildings almost certainly will harvest energy, and that seems to me an absolute given. It makes absolutely no sense to not harvest energy in the very places you need it. And the ability to make construction materials that also double as energy absorption and electricity generation is, again, totally doable. Aesthetically, one of the things I'm really looking forward to is thermochromics becoming part of the urban landscape. At the moment, thermochromics, so that's a material that changes color with temperature. Then in novelty items, you get them in mugs, and sometimes people make T-shirts and they change color and everyone laughs. But imagine a whole building changing color because it got hot. And because it changes to white, it reflects more heat and requires less cooling. I mean, you see this in the natural world. You see chameleons changing color. I think cities of the future changing to autumn colors, that will be a really exciting prospect.
Materials today are made in big quantities often, vats of concrete, crucibles of steel, whatever. Will it make sense then to assemble new custom materials on the molecular level or atom by atom? I mean, that's a lot of assembly. It's nice to say you're going to build some custom material one atom at a time, but is that ever going to be practical?
I mean, so when you look at biology, which already does this, protein by protein, carbohydrate by carbohydrate, you realize that to grow anything of any size, you need time. And perhaps the economics of our society will not allow us to wait around for a few years for a car to be grown that way. But I think for smaller objects of those components, an interesting thing which is coming so fast, it's so exhilarating at the moment, is how fast 3D printing is changing. And the idea that, which I really like, that you won't have to buy a whole new car just because one component of your car is now defunct and you can't find the spare part, will end. That the digital file of any component will be available and you can just print it off. Already the military are using this. That's how they're using it to get rid of supply chain problems. And 3D printing of objects on demand, perhaps even clothes, certainly any component in your house, I think that's coming.
Mark Miodownik, thanks so very much for speaking with us and giving us all this interesting material.
Pleasure.
Mark Miodownik is director of the Institute of Making at University College London.
Well, here we have it. I mean, today when we think of tinkering with molecular structures, it's mostly in terms of biology, using CRISPR technology or something similar to edit DNA to avoid or cure some disease. But there's just so much real promise in engineering at the molecular, maybe even the atomic level, to make stuff that's, super strong or doesn't need to be painted, maintained, cleaned, whatever. And so, yeah, sure, there's a problem scaling such things up to industrial quantities. That's hard. But hard things, well, they're only hard.
It's interesting that he gave examples of material science that are not drawn from nature. For example, carbon nanotubes and buildings that will change color. But even in that example, he compared the buildings changing color to a chameleon. So maybe you can't really get away from the biological examples that evolution has presented us.
Well, I mean, I guess that's a tribute to biology. But hey, it's been busy for almost 4 billion years, so maybe it's not so surprising that it's so surprising.
So in this century, we are going to see many new materials, all different kinds, smart materials, materials that are more flexible, that are so-called living materials.
Yeah, I think so. And just, the fact that you could build materials for building bridges, for example, that don't require maintenance, that kind of thing. Just think of what that might mean for society.
Are you looking forward to ingesting some protein derived from flesh-eating bacteria?
Listen, I don't have anything against those flesh-eating bacteria. They got to live, too. And besides, I'm a flesh-eating hominid.
Well, thanks to those who are not immaterial to helping us produce this show. Senior producer Gary Niederhoff, operations manager Barbara Vance, and intern Daniel Marino.
Thanks also to financial support from Rena Shulsky David and Sammy David, and to the William K. Bowes Jr. Foundation. Big Picture Science is produced at the SETI Institute, a nonprofit scientific and education organization whose scientists study the origin and nature of life, including the behavior of rings around planets. And a big thanks also to our listeners.
Your ears have been attuned to an episode of Big Picture Science called It's Immaterial. If you'd like to hear more Big Picture Science, well, you'll find episodes in our archive at bigpicturescience.org.
And if you're a podcast listener but prefer listening to over-the-air radio because, after all, radios allow you to tune in all sorts of interesting material, check out the listing on our website of radio stations that carry the program. And if your local station is not on that list, consider letting them know you like the show.
How do you like my soup?
It's pretty good, but it could use some more packaging.